We will talk about this a little later as we move on. Let's now talk about phase difference and path difference. Phase difference and path difference. Now, you remember we talk about the phase of two particles. If one particle, tell me, if by the time one particle completes one vibration, the particle on the left completes one vibration, the energy just reaches the particle on my other hand. Now tell me, what is the phase difference between these two particles? Particle 1 has completed one vibration. The particle 2 and particle 1 are now beginning together. I can say the phase difference is 2 pi. Is that right? Because particle 1 has completed, look at this, this is 0, pi, pi by 2, pi, 3 pi by 2, 2 pi, and now the two particles are beginning. A phase difference of 2 pi, what is the distance between these two particles now? The distance between nearest particles that are in phase is a wavelength. That means a phase difference of 2 pi equal to a distance of 1 wavelength. Did you understand that? Let me see if I can show that over here. If there are two particles, one here and one here, this one has completed one vibration. That means it has gone through a phase of 2 pi, and this is the second particle is now beginning to vibrate. Therefore, we say the phase difference between the two particles is 2 pi. Now, the phase difference between these two particles is 2 pi, means this has completed one vibration when this just begins. That means they are in the same phase of vibration. A phase difference of 2 pi actually means in the same phase. Now, what is the distance between these two particles? Is 1 wavelength. So, the distance here is 1 wavelength. So, 1 wavelength, a difference of 1 wavelength is equivalent to a phase difference of 2 pi. That means a distance of lambda by 2 is equivalent to a phase difference of pi. A distance of a quarter lambda is equivalent to a phase difference of pi by 2, and so on. When the distance between the two particles is a wavelength, the phase difference is 2 pi. If the distance between the particles is half a wavelength, here there's a particle here, the phase difference between those two particles will be pi. They'll be completely out of phase. If the distance between the two particles is a quarter of a lambda, the phase difference will be pi by 2. I want you to remember the relationship between the wavelength and phase difference. We will be using that as we go on in the next couple of slides. Okay. Now, if one wave starts from point A and another of the same frequency starts from point B, how do we know if they are in phase or out of phase when they meet at point C? Can you tell me, is there any way that you can tell if the waves from A, suppose this is loudspeaker 1, B is loudspeaker 2. Both the waves from speaker 1 and speaker 2 reach point C. Is there any way to tell whether those waves are in phase and out of phase? Alright? When a wave propagates in a medium, particles of the medium in intervals of 1 wavelength are in the same phase of vibration. That's what I was showing you a little earlier. Particles that are in intervals of one wavelength are in the same phase of vibration. How about particles in an interval of 2 wavelengths? They will also be in the same phase. How about particles in intervals of 5 wavelengths? They will also be in the same phase. For example, now if these are 2 particles, the distance between them is 1 wavelength, they will be in phase. If the distance between 2 particles is 5 wavelengths, they will be again in phase. Alright? If there are 50 whole waves in the distance from A to C, and 44 whole waves in the distance from B to C, I'm just giving you some numbers. Suppose there are 50 whole waves in the distance from A to C and 44 whole waves in the distance from B to C. Tell me, will those waves meeting at C, will they be in phase or out of phase? Well, they will be in phase because all whole number difference in wavelength will be in phase. In other words, if there are 100 waves in the distance AC and 200 waves in the distance BC, the difference between the two is 100 whole waves. That means they will be meeting in phase. So, if the difference between the paths taken by the 2 waves to reach C differs by an integer multiple of the wavelength. For example, if the difference between the path AC and BC contains an integer multiple of the wavelength, 1 lambda, 2 lambda, 3 lambda, 5 lambda, 50 lambda, and so on, then they will meet in phase at C. Now, what is the meaning of path to difference? Path to difference is the difference between the length of the path. So, if the path to difference between AC and BC is an integer multiple of a wavelength, then the waves from A and B will reach C in phase. You will hear a loud sound. So for any integer n, the condition for 2 waves to meet in phase, what is the condition? That their path to difference must be equal to n lambda, where n is an integer. N can be any integer, 1, 2, 3, 4, 5, and so on. So one more time, if the path to difference between waves from A and B reaching C is an integer multiple of a wavelength, then the waves from A and B will reach C in phase. On the other hand, what is the condition that they will be meeting out of phase or they will destroy each other? The condition for destructive interference happens when the path difference is an odd multiple of half a wavelength. Remember, I just showed you if the distance between 2 particles is half of a wavelength, they will be completely out of phase. So, if the waves coming from A and the waves coming from B, when they reach at C, if the difference between the path they take differs by an odd multiple of half a wavelength. Why do we have to have odd multiple of half a wavelength? Because when you take even multiple of half a wavelength, they will become integer numbers. Now what we need for destructive interference is that the path difference must be some odd multiple of half a wavelength. 1 lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. If the path difference is an odd multiple of half a wavelength, then the waves from A and B will reach C completely out of phase. And so we will say the condition for destructive interference is the path difference must be 2n plus 1 lambda by 2. 2n plus 1, where n is an integer, 2n plus 1 is always odd. When n equal to 0, this will be 1. When n equal to 2, 2n plus 1 is 5. When n equal to 4, 2n plus 1 is 9. So if n is an integer, 2n plus 1 will always be odd. The condition for destructive interference is, what is the condition? That the path difference must be equal to, an odd integer multiple of half a wavelength. That is the condition for destructive interference. For constructive interference, the path difference must be equal to an integer multiple of the wavelength. For destructive interference, the path difference must be an odd integer multiple of half a wavelength. Alright? Let's, you know that the path difference of lambda is equivalent to a phase difference of 2 pi. If there are 6 whole waves in the distance AC and 6.5 waves in the distance BC, then the difference, the path difference will be half a wavelength when they reach C. That means waves from A and waves from B will reach C completely out of phase, and there will be no sound at that time. That means a phase difference of pi is the same as a path difference of lambda by 2. A phase difference of pi by 2 is the same as a path difference of lambda by 4. I wrote down this for you in the beginning earlier on. Let's do an example. 2 sounds of the same frequency, 170 Hertz,